Today we're going to study congruence transformations. They're also called rigid motions. What do I mean by a transformation? Well, you might be somewhat familiar with the word already from, Saturday morning cartoons. These are a little different from the Transformers. Our triangles won't turn into snakes or fire-breathing monsters. In fact, they won't change into anything but triangles that are exactly like what they were before, except in a different position. In other words, they'll be translated or moved, like when you pick up a chair and put it to a different spot. When you move your desk or someone else's desk, that's a congruent or rigid transformation. That's also a translation. Rotation, I'll explain that in a minute. And reflection, well, that's pretty much exactly what you would expect it to be. It's kind of like what you see when you look at a still pond or a lake. You can see everything above the water line reflected from the water line down. Probably the simplest transformation to explain is the translation. We have a triangle here. Suppose I take this triangle and move a copy of it over and up. Who knows what I did with it. But I moved it. Okay, that's a translation. I can move it up here, I can move it there. Now, how would I describe this translation? Well, that's a good question. How would you describe this translation? Let's take a look. Now, let's say we have this triangle here, and we've moved it. So what did we do? Well, I've added an XY axis here, so we can actually count what we did. Now, the important thing to remember about all the transformations we're going to use in this section, everything moves the same way. This point, or vertex, this vertex, and every point on the lines in between all move exactly the same way. Whatever one point does, every single point in the object does the same thing. So all we have to do to figure out how we move this is to pick one point. But let's try the vertex up here. This is the point, let's see here, 6, 7, looks like 8. X is 8, pardon me, that's minus 8 of course, and Y is 2. Where did that point end up? Well, it looks to me like X is 9, and that's positive of course, and Y is 7. So what did we do? We moved this way 17 units. We move this way 5 units. How do we express that in our nice short mathematical notation? And we do it this way. XY goes 2. And what did this part here? This is called the image of the transformation. This is the original object. This is the image under the transformation. So, X plus 17 because we added 17 here. Or, in other words, we went 17 units to the right. And Y plus 5 because we went up 5 units. And that's the way we would write this. This tells you that for any given point, that point will shift 17 units right and 5 units up. And that's how we describe a translation. And I guess I should point out that in general terms, if we shift A units to the right, just tells you how far the x-coordinate shifts, and there's nothing stopping A from being negative. We could have gone to the left. In fact, if you want to reverse this translation, you would start here and go that way. You could write xy, let me put it down here, give myself more room, goes to what? X minus 17 and y minus 5. That'll push us 17 units back over and 5 units down and put us right back where we started. Here's what a rotation looks like. Suppose we have this triangle over here. This line I drew in, this is not part of the rotation. This is just an easy way for you to keep track of what the heck's going on. What we're doing here is rotating this triangle about the origin. And in this section, when we rotate, we're going to rotate about the point 0, 0. We could rotate about, say, the center of this triangle, and then it would just spin around like a pinwheel. We could rotate about some other point. In this section, we're going to rotate about the origin. And what that means is just pick some point to draw a line from the origin to that point on the object, and then swing, consider the line and the object as one rigid piece now as you swing it across this way. And this was, well, if we started here, then this is what? A clockwise rotation, which is negative. This is about 90 degrees. Might be a little bit more. I was shooting for 90, but I might have missed. But notice the triangle rotates just the way it would if it were connected to an arm that just swung around and it was all one rigid piece. And that's how we do a rotation. Notice for 90 degrees, you're going to have some easy ways of computing your new coordinates. For instance, this thing here will move to here. So if we were just, let's estimate this as the point 66. Okay. Right here. It's a little bit off, but suppose it was. Where would it move to? Over here? Oh, okay. I redrew this so it would make a little more sense. We have the apex up here at minus 6, 6. And the corner down here at about minus 7, 4 and minus 5, 4. Now the cool thing about these 90-degree rotations is that it's pretty easy to figure out where a point ends up, because you just switch things around. For instance, all we've done is change quadrants. For instance, in this quadrant, X and Y are both negative. In this quadrant, they're both positive. In this quadrant, it's positive. Oops. Positive. Negative. And in this quadrant, it's negative. And I goofed. This quadrant, of course, is negative, positive. X is negative, Y is positive, and this one is negative, negative. So what we do when we switch around here, since it's 90 degrees, that's the trick. We end up reversing things and choosing the correct sign. For instance, we reverse the 4 and the 7 here to get this point here. But it has to be positive because we're over here in the positive quadrant. If we went the other way, we do the same thing. We reverse the X and Y coordinate, but the X coordinate would have to become negative. And if we rotated it down this way, we do the same thing. As you change quadrants, you reverse the X and Y coordinates, and you change the sign according to this rule here. If it was already positive, leave it positive. If it switches, then you switch it. For instance, down here, you would make it switch, but you'd have to make Y negative and leave X the way it is. And our last form of rigid or congruent transformation is a reflection. We can reflect about two different axes in this section. Technically, you could reflect about any line. I could draw a line here and reflect this object about that line. We're just going to reflect about the x-axis or the y-axis. That makes it especially simple to find the coordinates for your reflection. Why? Well, for instance, if we reflect this about the x-coordinate, it's going to be just like I said before, the reflection in a pond. Well, this is the point 5, 2. Then this is going to be the point 5 minus 2. Here we are at 8, 2, 8 minus 2. And this is, looks like 6.5 and 5. And this is 6.5 and minus 5. So I wrote in the coordinates, and you can see exactly what happened as we reflected this about the x-axis. Well, coordinates stayed pretty much the same. We just made y negative. And if we want to reflect about the y-axis, well, we're going to do something similar, aren't we? Things will be about the same, but we're going to have to make x negative. So we can do this pretty easy, right? This point will become minus 5, 2. And be right about here. This point, minus 8, 2. Minus 6.52. Or 5, pardon me. Minus 6.5 and 5. So if we reflect about the y-axis, we have 5, 2, minus 5, 2, 8, 2, minus 8, 2, and like that. Very simple. So what's the rule here? How would we write this? Well, we just write that our reflection about the y-axis can be written as xy goes to minus xy. We just change the sign of the x-coordinate. Down here, reflecting about the x-axis, xy goes to x minus y. We just change the sign of the y-coordinate. So your reflections about the x and y-axis are fairly easy to work out. So now let's do some problems. Well, here's another one of those somebody made a mistake problems. I guess this is kind of a common mistake, I don't know. With transformations, there's so many ways to make a mistake. It's hard to pick one that's just standard. The error here is you can't switch around, so to speak. He's measured their angle from this vertex to the origin. Well, rather, he's drawn a line from this vertex to the origin. Now he's taken the transformed triangle and drawn a line from supposedly the vertex to the origin, but he used the wrong vertex. This is where the hypotenuse meets the short leg of the right triangle. This is where the hypotenuse meets the long leg of the right triangle. So, oops, pardon me. What he should have done is drawn the line from here to the same vertex. But he's not totally off, he just drew this line here. And then you measure this angle, which looks like 90 plus maybe 20 or something. Actually, I've got that wrong. It's not 90 plus something. It's a lot less than this anyway. If this is 120, this is pretty close to 90, isn't it? It almost looks like a 90-degree rotation. And does he say, well, the other mistake he made was saying that it was, oh no, that is clockwise. So we got that part right. Good for him. But it's not 120. It looks like it's closer to 90. So be sure to keep that straight if you're going to draw the line from the origin to some vertex of the polygon. Make sure you stick with the same vertex all the way. Well, you could probably do this one in your head. There we go. 0, 3 goes to 1, 2. So it's just like that little arrow we put in there. 0, 3 goes to 1, 2. The image of 0, 3 is 1, 2. If I didn't mention that, that's what we call what you get after the transformation. That's called the image. Very similar to functions, where you had your x and then the image. Same thing here. Don't know if you're used to doing it that way or stating it that way, but functions are frequently written as there's x and then the image of x under f at x. Well, same thing here. We have the transformation and the image of the transformation. Well, it looks like this went up 1 here, and from 3 to 2 it went down 1. So we've got 1 and minus 1. Looks like the y-coordinate went down 1. The x-coordinate went up 1. So we could write this as the image of xy is x plus 1 and y minus 1. So what would 2, 5 translate to? Well, that would be 3, 4. I don't think you'll have any trouble with this. Now, this is a lot like the last problem, except that we're just going to work backwards. We know the image is 4, 0, and the translation was x plus 2, y minus 3. So how do we go backwards? Well, that's pretty simple. What would you expect to do? You added 2 and subtracted 3 to get to the image, so if you want to get back to the original, what do you do? Well, I would say you would take x minus 2 and y plus 3. In other words, just do the same thing in reverse. So this would be the inverse of this translation. The translation moved 4, 0 to here. Well, actually it moved the entire object to the right 2 and down to the right 2 units and down 3 units. So how do we get back to the original? Well, we go down or left 2 units and then up 3 units, and that puts us right back where we started. And how do we do that with the point 4, 0? Well, we subtract 4. We subtract 2 from 4 and get 2. We add 3 to 0. And we get the point 2, 3. Would have been the original point if the image was 4, 0. Now we can check that. Suppose we apply this translation to 4, 0. We get x plus 2, that's 4. We get 3 minus 3, that's 0. So, yes, the image of this point would be 4, 0. See? Not that bad. Well, this looks more complicated than it is. At least I hope so. Let's see what's going on here. We've got AB to CD and then CD to EF. So, let's suppose that A transforms to C and B transforms to D. That seems to be the way they laid it out. So, under this transformation, we have that A goes into this. Well, what do we have? Well, the x-coordinate here would be 2 minus 2. What's the x-coordinate here? What I'm doing is applying this transformation to this. So the x-coordinate of the image should be x, which in this case is 2, minus 2. And that should be equal to m minus 3 equals 4. Or, pardon me, just plain m minus 3. Okay. So that's 0, and we get that m equals 3. We have m minus 3 equals 0, so m must be 3. What about over here? Well, we have 4. Oh, not quite. We have to do the y-coordinate, don't we? And wake up. And 3 plus 1 goes to 4, so that's okay. We didn't have any variables in the y-coordinate, so I guess we didn't have to do that. What about this one? 4 minus 2. Well, okay. We're doing the x-coordinate right now, because that's the one with the variable in it. So 4 minus 2, because that's what the translation does, equals n minus 9. And I get 2, let's see what we got here. This is 2 equals n minus 9, or n equals 11. Okay. What about over here? Now we've got a variable in the y position. Now let's try the y's over here. So we get 2a, apply our transformation, which is to add 1 to it, and that put us at 5. Subtract 1 from each side, we get the 2a equals 4, or a equals 2. So we've got a, m, and n. Well, now we can put our new values in here and figure out which points are going into these two images. Let's see here. M is 3, so this is 0. And this is still 4, of course. We've got n minus 9, which is n is 11, so this is 2. Now our second transformation. Remember, that's okay. We can apply transformations successively. Our second one is a reflection. What does a reflection do? Well, I'll write it over here. Remember, this one's about the x-axis, they say. Which means, if we were to draw a quick little coordinates over here, what does it mean to flip it about the x-axis? It means we just change the y-coordinate to, in a sense, the opposite of whatever it was. If it was positive 3, it becomes negative 3. If it was negative 3, it becomes positive 3. Pretty easy. So over here, it looks like, well, just like I said, the x-coordinate's not going to change. So 0 goes to 0, nothing to do there. Well, 4 goes to minus 4. So the second coordinate has to be minus 4. So now we can find g by writing minus 4 equals g minus 6. We add 6 to each side and get that g equals 2. Down here, well, we have 2, 5 goes to 8h minus 5. Makes sense so far. Like I said, the y-coordinate just changes sign, and the x-coordinate doesn't change at all. So now we can write 2 equals 8h. And implies that h equals 1/4. Well, it looks to me like we found G, we found H, we found A, we found M, we found N. I think that was everything. And these over here should be the point 2 minus 5. And this, of course, is 0 minus 4. And this one, if anybody cares, would have been the 0.44. Well, as I say, it looked kind of messy, but it was really just a whole bunch of simple equations. What did we do here? Like 5 very simple equations to solve for 5 variables. It's just like doing the same simple one-line algebraic equation 5 times. Just change the numbers around a bit. Now, I'm sure you had no trouble with this one. Well, this one's kind of cool if you like chess or wanted to learn about it. If you hate chess, then I guess you're just stuck with a boring problem. What is it they're asking us to do here? Well, first they tell us how the knight moves, just in case you're not sure. Not everybody plays chess. And they tell you it's 2 in one direction and then 1 perpendicular. So you go 2 that way and 1 that way, 2 that way, 1, and on and on. There's another way to describe the knight move, and that is 1 straight square and 1 diagonal square. Works out the same. 1, like that. That's 2 and over. A lot of people think of it this way. Some people think of it as 1 square along a row or a column, and then 1 diagonal. You end up in the same spot. Describe the transformation used by the knight to capture the white pawn. Well, that explains why they described it as 2 up and 1 over, because the diagonal is something we're not too good at defining yet. So, describe the translation used by the black knight, this one here. What did he do? Well, let's start by okay, now we know we've got xy getting translated to something. X looks like he went to the left, which is negative for x, right? So that's x minus 1. And the other one is y plus 2. I guess you could live without the parentheses in the middle. Sometimes I do that when there's multiple terms between the commas, just to keep it straight. I guess they don't usually do that, and they probably don't do it much in your book. Same thing. I could have just written it this way, I guess. X minus 1, comma, y plus 2. Like that. You get the idea. That's the transformation used by the black knight to capture the white pawn. And how about the white knight capturing the black pawn? Well, I would say, I bet you would too, x is plus 2. So we got x plus 2. Move over that way, and then down 1. That's all you had to do. Just, if you can count, you can probably figure these out. Just have to keep track of what a translation or a transformation is, that's all. In this case, it's a translation transformation. Now, after both pawns are captured, can the black knight capture the white knight? Well, the black knight would be here, the white knight would be here. No, there is no transformation that goes 2 in one direction and 1 in the other that would end up right next to it. You can't do that. However, he says, can the black knight capture the white knight? He doesn't say on the next move. If, we're talking black knight captured, okay. Suppose the white knight just sits there, and the black knight goes from here to here. Okay, you can do that. That's a legal move. And then he goes from here to here. Well, so he'd have to land on his own pawn, wouldn't he? So he couldn't do that. Suppose he goes from here to here. Then he could go from here to here. That wouldn't work either. Sorry, I play enough chess to know that the knight could capture the other knight in a couple of moves, but I'm laying it out all wrong. Here's the black knight after the moves, and here's where the white knight would be after the, let's call them translations. Now, can the knight here capture this knight? And the answer is yeah, but it takes a couple of moves. He can move this way. That's, you could say down 2 and over 1, and then up 2 and over 1, and now over 2 and down 1. See, he goes this way, and then this way, and then this way. So he could, in fact, capture this knight, but it takes a few moves to get there. And in fact, you get down to it, with this kind of transformation, I don't think there's any square that the knight can't eventually end up on. That's not true for something like a bishop. Bishops are restricted to whatever color they're on to begin with. This black square bishop will always land on a black square. No place else he could ever go. These knights, on the other hand, they alternate. You see how that works? He's on a white square, he ends up on a black square. His next move would put him on a white square, and then a black square, and then a white square. And it goes back and forth like that always with the knight moves. Not very important in this class, but it's worth remembering if you play chess. Now here's one that, well, it looks kind of tough, but I think that's only because it is kind of tough. It's not immediately obvious what the original figure would have been. So what we have to do is work backwards. See, what they're asking us to do is assume that this transformations have been applied successively, a rotation and then a translation. And we wound up here, these 3 points. Now what we want to do is find out, how do we get back to where we started? Well, we just do everything you did to get there in reverse. Makes sense. First time you find the school, how do you get home? Well, you just do what you did to find the school, but do it in reverse order. Same thing here. Not only do we have to go 3 units down rather than up to reverse this transformation, and we also have to go clockwise, not counterclockwise. We went counterclockwise the first time, which would be that way. To reverse that, of course, we have to go clockwise. Well, I did part of it here already. Just save a little time, and yeah, it's kind of messy, but you get the idea. In order to reverse things, first thing we have to do is drop 3 units down. That'll get us halfway back to where we started. When we do that, we drop everything 3 units. The point -1,6 goes to -1,3. This is the point -1,4. That drops down to -1,1, and -4,4 drops to -4,1. I think I've mentioned a few times before, with these transformations, the important thing is to find out where the vertexes go. And then just, if you're working with polygons, the important thing is to find out where the vertices go. And then just, when you've transformed them, connect the dots. If you've got something else, a curve, it's a little tougher. We'll do that in another class. This class will be transforming polygons. See? We're not making you as miserable as we could. We're doing it the easy way. We're only working with polygons. What we have to do next is rotate this. Which way? Well, started out, we got there by going counterclockwise. So we have to get back by going clockwise. And this is unfortunate, the way I drew these numbers over here. Maybe I should change that. There we go. I moved some of these labels over so we can, coordinates. This is the point minus 1, 1. Minus 1, 3. It's right here. And minus 1, 4. That's this point here. Minus 1, 4. Drop down to minus 1, 1. Okay, we've got this part covered. What about our clockwise rotation? Well, that just changes our quadrants, doesn't it? Everything from this quadrant. That's because it's 90 degrees. If it wasn't 90 degrees, we'd have a problem in terms of exactly determining these coordinates. But as you can see, we're just switching everything over to another quadrant. Remember that? Over here, in terms of xy, we got everything's positive. Over here, it's negative, positive. Down here, it's negative, negative. And here, it's positive, negative. In other words, x and y are both positive, x negative, y positive, x, y are both negative, x positive, y negative. So when we make this switch over here, what are we doing? Well, it looks to me like we reverse. It's not quite like a reflection. We're going to have to do some other things too. For instance, this one here. This is going to go way over here, and we'll reverse things to 3, 1, won't we? And so as we rotate from one quadrant to the next, how do these coordinates change? Well, it's kind of simple. We've got minus 1, 3 here, right? That means we go minus 1 in the x direction, and then up 3 in the y direction. Well, when we switch coordinates, we're going to do a little switching here. Pardon me, when we switch quadrants, we're going to do a little switching of coordinates. For instance, we've got minus 1, 3 here. As we bring this down, instead of 3 units up, we go 3 units out. That's x equals 3. But this was 1 unit to the left. Now that's going to be 1 unit up. So we got 3, 1. So we went from minus 1, 3 to 3, 1. Well, look at here. Coordinates here are negative plus, right? And they're plus plus. And what did we do? We went, sort of, from negative plus to plus plus. But we also had to reverse. The y coordinate became the x coordinate became the y coordinate. What about down here? The point negative 1, 1. Well, same thing as over here. Instead of 1 unit to the left, it's 1 unit to the right, and then 1 unit up, and 1 unit up. So here, what did we do? Well, you could say we reversed them and then changed the sign, but since they both have the same value, it's not that obvious that that's what happened, is it? What about this one here? Minus 1, 4 goes into 1, 4. Well, once again, it looks like we swapped the coordinates and changed the sign on the x coordinate. And not only looks like that's what we did, that is exactly what we did. So, notice that our horizontal line with a 90-degree rotation becomes a vertical line, and our vertical line becomes a horizontal line. So, the answer, as it turns out, after all this, Yes, we've actually arrived at an answer. The question was, what was the original object? And all we really need to find is the vertices. As I've mentioned before, we just connect the dots once we find the vertices. And the answer is 1, 4, 3, 1, and 1, 1. Would the final image be the same if the original triangle was translated 3 units up and then rotated 90 degrees counterclockwise? Well, that's an interesting question. What would have happened? Well, if this thing rotated over here 90 degrees, we'd have gone from minus 1, 6 to 6, 1. And we do it algebraically over here. Okay? Since now we know what happens when we rotate, what happens to the coordinates. Minus 1, 6 would go into 6, 1. What do we have here? Minus 4, 4. Well, that would just go into 4, 4. Minus 1, 4. Well, that would become 4, 1. Now, we apply. In other words, when they ask, what they're asking here is, suppose we did it in the opposite order, in a different order. When we go back the other way, would it make a difference? Well, let's find out. That is what we're finding out, because now we're going back the other way. The first time we did it it was rotated and then up. That was the original transformation. Then we reversed it and went down and then rotated. And just to add to the confusion, let's figure out what would happen if we had first translated up and then rotated. So what would have happened? To go backwards, we would have to rotate and then go down. So these are our new coordinates after we've rotated 90 degrees. Now we have to drop down. And I think you can see right off the bat, we're not going to end up in the same places. Not even close, really. When we drop down 3, this will become 6 minus 2. This will be 4, 1. And this will be 4 minus 2. And if you're wondering why, or another way of looking at it as to why this doesn't work, it matters which order you do it in. Consider this thing here. Now if we rotate this 90 degrees, we got a line here from here to here. That 90-degree line is going to go way out there. When we drop down, we're going to end up over here somewhere. In other words, this is a longer arc, so it's going to move farther, and then when we drop down, we're messed up. Well, that's it for now.